pointillist printing, quantum physics, the world of the small, the ultra-small, and the very uncertain. This time on Science Without Walls. Welcome to our concluding program on physics, from Newton to Quanta, from the world you and I know to the world of the ultra-small, the realm of the quantum. Our world, our universe, consists of matter and energy. The matter is grainy because it's made up of individual units called atoms. If we could see at a high enough magnification, and we can with special microscopes, we extend our senses, we can actually see images of individual atoms. Everything has a structure, a fundamental unit. Magnify a photographic negative, and you see the individual silver grains which make up the image. Or magnify the dot matrix image from a computer printer, or a newspaper photo, or even a Seurat painting. Everything is made up of building blocks of basic units and the basic graininess of matter. Its fundamental units, atoms. You've let me use the analogy that the atom is like a miniature solar system, with the nucleus representing the sun, the electrons representing the planets. But remember Einstein? Well, he said, science should be as simple as possible, but not simpler. Well, let's get realistic about atoms. Atoms are small. The size of a little atom, like hydrogen, is about 1 angstrom. That's a new unit, devised specifically because atoms are so small. An angstrom is 1/10 of a nanometer. So an angstrom is 10 to the minus 10 meters. Planets have masses, different masses. Electrons all have the same mass. Planets and the sun are held to each other by gravity. But the force of gravitational attraction between the nucleus and the electrons and atoms is insignificant because their masses are so incredibly small. Electrical repulsion and attraction are the forces in atoms, together with the nuclear forces that hold all those protons together, overcoming the force of electrical repulsion between like charges in the nucleus. The atom is nothing like the solar system. The reason I've lied to you a little about atoms is because of the way you are neurally wired. It's hard to make new connections, to learn something new, unless you can somehow relate it, connect it to what you already know. That's why we use analogy and metaphor. Picasso perhaps said it best. So how do you go about teaching them something new? By mixing what they know with what they don't know. Then when they see in their fog something they recognize, they think, ah, I know that. And then it's just one more step to, ah, I know the whole thing. And their minds thrust forward into the unknown, and they begin to recognize what they didn't know before, and they increase their powers of understanding. Picasso was a painter. Paintings manipulate light, light which you sense and perceive. Much of what we know about the nature of atoms comes from an analysis of the light, the electromagnetic waves they can produce. Luminescence is the production, the generation of light photons. See, light seems to have two limiting characteristics. Some of its behavior is best explained using a particle metaphor, and those particles are called photons. And other properties are most easily explained using a wave model, an electromagnetic wave. Light is photons, and it is electromagnetic waves. We focus here on visible light because we can see it, but we also have X-ray luminescence, producing X-ray photons, and radioluminescence, that's photons in the radio frequency range of the spectrum. Normally, when we use the word luminescence, we mean the generation of photons which humans, you and I, can perceive in that 400 to 700 nanometer wavelength range. Light rays, light photons, carry energy. Blue light has more energy than red light. And there's an even more energetic form of light, an ultra-blue light, which you can't directly see. We call it ultraviolet, and it's also called black light or UV light. Each individual UV photon has so much energy that it can produce a chemical reaction, a chemical change. Enough UV photons and you get a nasty sunburn. On the other end, beyond the red, the spectrum is called the infrared. You can't see that either. And in low amounts, it's of course not dangerous. But you can feel it through the heat, through the infrared receptors on your skin. If we get atoms really hot by putting them in a hot flame, they produce light. They luminesce, and they produce very specific colors, specific wavelengths. Different atoms produce different colors. So can we analyze atoms by looking at the colors they produce? Can we look at light from the stars and learn something about the atoms in those stars? Is there more to light than just the three major colors that we see in rainbows or prisms? The answer to all of these questions is a wonderful yes. Prisms and gratings can be used to see far more than just the primary colors. They can be used in spectrometers, in instruments which break up light very finely, disperse it very accurately, and allow us to see the individual colors, the individual wavelengths in a mixture of light. There are lots of spectrometers at the University of Utah. Here's one in Dr. Vladimir Chladi's lab in the Department of Bioengineering. He's kindly taken the top off a large spectrometer so we can see it working, how the light enters. He's using a special light source which has most of the colors. The spectrometer disperses it into its component colors, individual wavelengths. Instead of a glass prism, it uses a diffraction grating which separates the light into its component wavelengths. You see that here, reflecting off a white card. You can use such a machine, a spectrometer, to look at the colored flames produced by the elements we saw earlier. Every element has its own characteristic emission. Lots of discontinuous, isolated, sharp or narrow wavelengths of light. So narrow we call them lines. Spectroscopists call these line spectra. And these spectra, because they contain the highly individual specific colors or lines, tell us that light emission is specific. Well, why isn't the spectrum continuous? Well, somehow the electrons in atoms are arranged or organized or structured in such a way that they generate these highly individual, specific photons. These emission spectra are the fingerprints of the atoms. 3 key experiments enabled physicists to begin to understand light and quantum physics. One was the line spectra of elements, their light fingerprints. And the second key experiment was the discovery of the photoelectric effect, the discovery for which Einstein was awarded his Nobel Prize. The photoelectric effect has to do with the energy of photons and clearly separated the ideas of energy and intensity, that is, the number of photons. You see, it's not just the quantity, but the quality, the energy that's really important. And the third key experiment used radiation emitted by hot black material, what physicists call black body radiation. And that does have a continuous spectrum. Most physics classes go into these 3 key experiments in some detail. We just don't have the time to do that here. A fellow named Max Planck went way out on a limb. He suggested that these 3 key experiments could be interpreted by assuming that there is a fundamental graininess to energy, a very tiny number, now called Planck's constant, h. is related to the smallest amounts of energy which can exist. Planck's constant, h, equals 7 times 10 to the minus 34 joule seconds. It refers to energy in time, so its units are joule second. The fundamental graininess is not really energy, but energy in time. A good physics class will probe into this in a little more detail. Again, we just don't have the time here. But I must tell you a related deduction of modern physics. The fundamental energy of a single photon, and that's E equals h times nu, Planck's constant times frequency. So each individual photon is a tiny independent packet of energy given by h nu. Sure, we can have many such photons, all of the same frequency or wavelength, but the total number of these photons is the intensity of the light, and each individual photon has the same energy given by h nu. And since we know that lambda, the wavelength, times nu is c, the speed of light, we can also say that the energy is h times c over lambda. So we can figure out the energy of a photon if we know its wavelength or its frequency. You know that the fastest thing we know is the speed of light, c. Nothing can go faster than 300,000 kilometers per second. The smallest things we know are the fundamental units of photon energy, the fundamental energy graininess in the universe, and that's related to Planck's constant. Therefore, the greater the frequency nu of a photon, the greater its energy. Blue photons have shorter wavelengths, larger frequencies, so they have more energy in each individual photon. So if it takes a certain minimum energy to do some chemistry, or to kick an electron free from a metal, for example, then it's clear that some photons have what it takes and others just don't have what it takes. It's not the number of photons that count, it's the energy in each individual photon. We've seen graininess before, in our currency system, for example. The penny is the Planck constant of our monetary system. You can't price anything less than a penny, at least not practically. Pennies are completely negligible and irrelevant if you're a millionaire or a billionaire. In the realm of the big world, the macro world, the Newtonian world, Planck's constant, and even individual atoms are unimportant. We are big, massive bodies, and we don't have to worry normally about individual atoms or subatomic particles or fundamental minimum units of energy. But as we go away from the macro world that we know and love to the micro and submicro, to the level of the atom and the individual photon, then of course these fundamental limits start to become important and we can no longer ignore them. Newtonian mechanics, the laws which describe the stability of the solar system, or these bouncing balls, do not directly apply to the level of the atom and to individual photons. Atoms and photons must be treated by a different part of physics, called quantum physics. You know, it's strange that in literature and poetry and politics, a quantum leap or quantum jump is considered a huge, significant thing. But in the world of physics, a quantum is the smallest piece of energy we can ever have. Interesting. Okay, so just how do atoms produce specific kinds of light, specific kinds of photons? Well, back to a more realistic model of atoms and of electron orbits. Electron orbits are not precise planar orbits. First, they're three-dimensional. Second, they're a little fuzzy, not really very precise. And third, they can sometimes have strange and convoluted shapes, although they are always symmetrical. We're not going to worry about the details here, but I must tell you that the electrons around the nucleus of an atom can't occupy just any orbit. An electron, to be stable, has to have associated with it a certain amount of energy in a particular orbit. Exactly what those electron energies are and the particular shape and location of the orbit depend on many things, including the nature of the nucleus, the fact that electrons themselves behave with wave-like properties. But the bottom line is that the electrons in any particular atom are in fairly specific orbits of fairly specific energies. Here we simplify the picture to focus just on the energies. The orbits are quantized. That means we can't put the electron anywhere. Only certain locations or orbits will work. Intermediate orbits are just not allowed. We can't put an electron here, for example. It will just go somewhere else to an orbit which is allowed, in which it is stable. But even with these restrictions, there really are many, many different orbits for electrons and atoms. There are even large numbers of orbits in which there are no electrons. You could call them virtual orbits. We call them unfilled orbits. And if we give an electron just the right amount of energy, we can put it in one of those unfilled orbits. We could also give it enough energy to bust it free of the atom altogether. Physicists and chemists, they can do all these things. By removing an electron from the orbit in which it would otherwise be located, we cause an instability in the atom. So an electron in an orbit further up in energy falls down to that lower energy orbit, which is now vacant. And to be stable in the vacant lower orbit, that electron has to give up a specific or quantized amount of energy. And it does this by emitting a photon. Since a very specific amount of energy had to be given up, a very specific photon with a particular wavelength and frequency is emitted. We can also excite electrons into higher unfilled orbits. We can heat atoms, give them so much energy that they vibrate so hard that electrons are actually thrown into upper, unoccupied orbits. And then those same electrons, or maybe other ones, jump down to fill those now vacant inner orbits. And every time an electron jumps down, it has to get rid of its excess energy, and it gives off a photon. Some atoms, like uranium, have as many as 92 electrons in very complex sets of orbits around a nucleus with 92 protons and over 100 neutrons. So electrons can bounce around between orbits, and the higher unfilled orbits too. And every time the electron comes down in energy, it must give off a photon. And it's those photons which are the characteristic emission spectrum, the light signature or fingerprint of excited atoms. The natural world is quantized, meaning everything happens in discrete little chunks based on h, Planck's constant. In the case of light or electromagnetic radiation in general, we call those chunks photons. They're packets of energy, but not just any energy. From the spectra of the elements, scientists have figured out the structure of atoms and the nature of the electron orbits in atoms. And once understood, once we had this big catalog or database of the emission spectra of all the atoms, we could use it to search for atoms in other places, like the stars. And that's how we now know the composition of the stars, of our sun, and the composition of other unknown materials. But now comes the fun part, the part that older Newtonian physicists really don't like. The fact that subatomic particles are so small and that the basic graininess of photons, of electromagnetic energies, is so very small, means that almost anything that we do to try to observe or measure individual atoms or photons changes them. If you use a single individual photon or electron to probe, to touch, to interact with, and thereby obtain information from another electron, proton, or photon, you've got a problem. The finest, tiniest, smallest things we have, electrons and photons, are of the same size and dimensions as what we would like to measure. It's like trying to see where a billiard ball is by hitting it with another billiard ball. The ball, your probe, is just too big or too energetic. The probe disturbs, moves the ball you're trying to measure. Whatever we do disturbs the system we're attempting to sense. There's just no way out. This is the uncertainty principle, first stated by Werner Heisenberg, and it says that the intrinsic graininess of things means that there's a graininess to the accuracy with which we can measure things. If there wasn't such a limit, then nothing would make sense. It would be like saying that the penny is our fundamental unit, yet I can determine price or value by tenths of a penny, or thousandths of a penny, or even millionths of a penny. And that's simply meaningless. How can we measure something to a precision that's smaller or finer than the smallest or finest thing we know? This intrinsic uncertainty in the nature of the atomic or subatomic world bothers Newtonian physicists because they're used to working in a macroscopic world, a Newtonian world, in which position and energy can be determined very accurately. But if there's a graininess in mass and a graininess in energy, then of course there has to be a graininess in measurement. There's no way out of it. It doesn't bother most scientists, and it need not bother you. So here's the present situation in physics, looking at the world in terms of dimension, space, and speed, or time. Things which you and I can see and deal with, even at the limits of resolution of the optical microscope, fall into the realm of Newtonian physics, unless they involve very rapid velocities, 1,000,000 meters per second or more. And this is where velocities start approaching the speed of light. When you're operating at velocities a few percent of the speed of light, or faster, then you have to apply a whole different theory of physics, called relativity, which is what Einstein is best known for. And we don't have time for relativity. And since it's unlikely you or I will ever go that fast, we just won't worry about it. As things get very small into the atomic and photon world, then of course we are in the quantum regime, where nothing is continuous or smooth. The basic graininess of the world means that mass and energy have to change in certain discrete amounts. In the case of energy, that discrete amount is the quantum, based on Planck's constant. In the case of mass, that discrete amount is the atoms and their subatomic particles. Since electrons and electromagnetic waves operate at the speed of light, much of the quantum world also requires relativity theory. So there are 4 general domains of physics, depending on the size and speed of the system. Most of your world, and certainly mine, is the area of slow-speed Newtonian physics. One bottom line from quantum considerations is that because of Heisenberg uncertainties, we just don't know things absolutely. Rather, we know things to certain probabilities. Depending on the specific problem and situation, everything is somewhat statistical. But it's important not to overplay quantum uncertainties. Even though we may not be able to predict the position of individual electrons or even individual atoms with the certainty that some physicists would like, we can deal with large collections of electrons, photons, and atoms with very great precision and accuracy. When you look at individuals or very small numbers, things are uncertain. But statistics, when you look at very large numbers, things can be very precise and predictable. Here's a quotation from Richard Feynman, who received the Nobel Prize for his work on quantum electrodynamics, the theory which predicts the motions of electrons, how they interact with each other, how they interact with photons, and how they produce photons. Feynman has been called the greatest mind since Einstein. And like Einstein, he was a very popular and charismatic character. In his beautiful little book, The Character of Physical Law, he writes, "I am going to tell you what nature behaves like. If you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing. Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. Nobody understands quantum mechanics." Well, that's it for physics. It's time to move on. If you found these physics programs interesting, maybe even fascinating, remember, this course is only a taste. Take a physics course, attend some lectures, watch some wonderful educational videos, read, discuss, and enjoy the basic rules of the universe. Remember our physicists in the wild? Well, next time we'll meet up with some chemists in the wild, and we'll begin looking at science from the perspective of chemistry. Richard Feynman is one quantum physicist who obviously enjoys the Newtonian world. He was also quite a bongo player and a pretty good artist. We'll catch you next time.